Hey everyone, today we are here with a double integral which is I equals to 0 to 1, 0 to 1, ln x, ln y and ln 1 minus xy dx dy. Well, before we are trying to solve this, we should know that ln 1 minus x equals to minus sigma n from 1 to infinite x to the power n over n, where absolute value of x less than 0, we can use this formula. So when we apply this one for there in that above equation, we get 0 to 1, 0 to 1, ln x, ln y. Well, these things don't change, so we can actually put parentheses minus sigma and from 1 to infinite. Because we have x, y there, so we should put x to the power n, y to the power n over n and dx dy. Let's give this minus and sigma form outside of the integral, and we are left with minus sigma n from 1 to infinite 1 over n parenthesis 0 to 1 ln x dot x to the power n dx and 0 to 1 ln y to the power n and dy parenthesis. Well, these both are the same, so we can actually do one integral first and we can similarly do it for the other one. So let's get with it. Equal minus sigma n from 1 to infinite 1 over n. If we integrate this first one, we get xn to the power x to the power n plus 1 over n plus 1 dot ln x 0 to 1 minus 0 to 1 x to the power n over n plus 1 dx. We can similarly do that for the y part also, so we will get the same answer. First let us solve this first one. This actually becomes pretty much 0, so we are left with, I'm going to put straight away this minus and this minus will cancel each other out, so it becomes plus. So we can write this as sigma n from 1 to infinite 1 over n and integral 0 to 1 x to the power n n plus n dx dot 0 to 1 y to the power n n plus 1 dy. Okay, cool. Now let's do some integration here. Sigma from 1 to n over 1 over n. If we integrate this, we can get x to the power n plus 1 over n plus 1, and we put those values there, so we'll get 1 over n plus 1 whole in square. We get the same answer for this ones also, so n plus 1 whole in square. So let's move on to page number 2. We have sigma n from 1 to infinite 1 over n times 1 over n plus 1 whole in to the power 4. Well, if we do some little partial fractions here, we get equals sigma n from 1 to infinite. Let's put a bracket here. We get minus 1 over n plus 1 over n plus 1 plus 1 over n plus 1 square plus 1 over n plus 1 cube plus 1 over n plus 1 to the power 4. That's it. Now if we give those sigma inside of this, we get, then I'm gonna do some max here. Means I'm gonna take that minus sign out of the equation, so I'll get left with minus sigma n from 1 to infinite and 1 over n minus 1 over n plus 1. Okay, Now if we give those sigma back to other terms individually, so we'll get plus sigma n from 1 to infinite 1 over n plus 1 square plus sigma n equals to 1 to infinite 1 over n plus 1 cube plus sigma n from 1 to infinite 1 over n plus 1 to the power 4. Well, to the first one, we should know that digamma of x plus 1 is equals to Euler's Mascheroni constant minus plus sigma n from 1 to infinite 1 over n minus 1 over n plus x, which is equals to Euler's Mascheroni constant plus nth harmonic function. We can write this as well. So we can see that where if I plug x equals to 1 and I get the same function above here. So if x equals to 1, then digamma of 2 is equals to minus gamma plus first harmonic number, which is minus gamma plus 1. You know harmonic function. This is we call harmonic function, which is 1 plus 1 over 2 plus 1 over 3 plus like that. So this is the first harmonic number, this is the second one, this is the third one, and it goes on forever. So digamma of 2, now we know that minus gamma plus 1. Okay, cool. So let's plug on those two. So you can see that this part here is actually this part. So we have digamma of 2 is equals to minus gamma plus sigma n from 1 to infinite 1 over n minus 1 over n plus 1. Well, here's this part. So we can actually plug there. Now we can write that to this above part. Wait, let me erase this. So this part we can write there as minus digamma of 2 and plus Euler's Mascheroni constant plus, well, you can see that this is what we have known as zeta function of 2. Well, zeta function, if you don't, some of them may don't know, so let me write that as well. Zeta function is we known as zeta of x is equals to sigma n from 1 to infinite 1 over n to the power x, where x greater than 1. So we know that zeta of 2 is equals to n from 1 to infinite 1 over n square, which is 1 plus 1 over 4, goes forever. And zeta of 3, same as that. This is we known as Apéry's constant, n from 1 over 1 over cube. This is equals to 1 plus 8 plus 1 over 27, and it goes on. And we have zeta of 4, similarly, n from 1 to infinite 1 over n to the power 4, which is equals to 1 over 1 to the power 4 plus 1 over 16, and it goes on. But when we plug those values here, we can see that it starts with, if I plug 1 here, it actually becomes 2. So 1 over 2 square equals to 1 over 4. It means every terms here, this one, and this one, starts with the second term onwards. So we can write these formulas as, wait, let me get on with it. We have minus digamma of 2 plus Euler's Masonic constant, and we can write this as plus zeta of 2 minus 1 because we are cancelling the first term out, plus we can do the same thing, zeta of 3 minus 1 plus zeta of 4 minus 1. Well, we know that digamma of 2 is equals to minus gamma plus 1. So this Euler's Masonic goes there and it actually becomes digamma of 2 plus 1 is equals to 1. So we finally can get the answer minus 1 plus zeta of 2 plus zeta of 3 plus zeta of 4. When we add those minus things out there, minus 3. So we have a final result where zeta of 2 plus zeta of 3 plus zeta of 4 minus 4, which is a gorgeous looking result we have here. Pretty neat, isn't it? Okay, then that's it for tonight. Let's find more integrals and more unknown equations from other integrals. That's it. Bye guys, let's see you in another video.